Welcome to our discussion on displaying data. The only thing we're going to look at today is how to interpret different types of graphs and kind of how to create them as well. Once you've gathered your data, the next thing you want to do is be able to communicate those results to other people, and just giving them a bunch of numbers usually isn't good enough. Human beings are visual creatures, so we like to be able to visualize things, so it's nice to be able to convey your results visually with graphs or tables. So our first kind of a visual representation of data is what's called a frequency distribution, and it simply is just a little table that gives you the count of every data value that you have. So like a 3 shows up 12 times, and a 5 shows up 10 times, and so on and so forth. Here's a simple example. It shows the number of crashes with roadside objects along a certain highway. Now you'll notice that there are two numbers, a number and then a thing in parentheses, but then the title tells you that this is a percentage of the total. So this is a kind of an augmented frequency table. It gives us frequency, but then it also gives us percentages, which in technical terms is a relative frequency. So sometimes you'll hear a relative frequency table being described, and when you have relative frequencies, you have percentages. Would you put the percentage symbol on this? Absolutely, you could. You don't have to, right? It's kind of, since it's up here, it's understood that this is 15.36%. And that's 57 absolute crashes that equals that percentage. And then you just scroll down through the table. Obviously, if you're going to, present these results to an audience, you'd want the entire table on one slide or on, one page if it was a report or something like that. But once we have this kind of information, we can answer all sorts of questions like, what do the numbers in the parentheses represent? Well, we know that they're percentages. We already talked about that. And we know that based on this little kind of legend that they give us telling us what they are. So you always want to make sure you do that if you are presenting your data in anything other than a very obvious kind of standard way. Which roadside object was involved in the most crashes? Well, because the guardrail category has the highest frequency listed, and if you didn't, kind of pay attention to all of them as we were going through them, which I'm sure was easy to miss, there's 15% and 57, and you can see that there are no numbers higher than 57, right? So that's the worst. How many total crashes did it cover? Well, we would have to add everything up, right? Add those, and those, because I repeated that one, right? So add all those numbers together, you get 371 total crashes, which is what you would need to calculate those percentages anyways, because you would need to take each number and divide it by 371. Okay, here's another example. They went and asked 52 families how many household pets they have, and then they just wrote down the numbers. So this family had none, this family had 1, right? This family had 2, and so on and so forth. Well, now we can put that data in a nice little table, and we had 0 through 6 as being our answers. If you look through here, you can see a 6, right? There's nothing bigger than a 6. And then out of those 52 households, 16 of them didn't have any pets, 15 had 1, and so on and so forth. So this is a nice little visual way of seeing what's going on, and it helps us answer questions like, what's the most popular number of household pets? Well, 0. 16 of the families had none. Second most popular, 1. This is just coincidental that as the number of pets goes up, the numbers go down. It obviously won't always work like that. Let's see, what else do we have? In a grouped frequency distribution, the data is grouped into different categories called classes. We normally do this when our data is continuous instead of discrete, right? So in this previous example, we had discrete data, meaning we were counting things. How many things do you have? That's discrete. Anytime you count, that's discrete data, because the data you gather, the answers you get will be simple whole numbers, right? Integers, 0, 1, 2, and so on and so forth. Nobody's going to answer, I have 2.5 pets, right? I mean, what the heck is that 0.5 of a pet mean? But if you're measuring things like what are your heights, what are your weights, those types of things, those are continuous variables. And because of that, you could literally get an infinite number of responses to the question. So you couldn't list every single individual number and its frequency, right? You wouldn't want to list, 55, 55.1, 55.11, 55.2, and so on and so forth. So instead, you would create these classes. You would give yourself a range. And you would do something like, 50 to 59, 60 to 69, and so on and so forth. And each of those little ranges, those little intervals are called classes. And then the class width is just how wide it goes from bottom to top, right? So if we go to 50 to 59, and then the next one starts at 60, that technically has a class width of 60, because you're thinking, well, 50 to 59 is just a width of 9, but it actually isn't, because you've got 1 through 9 plus 50, there's 10, so there's your class width of 10. I might have said 60 before. I'm sorry if I did, misspoke. The easiest way to figure out class widths is to look at the differences between the lower class limits or the differences between two upper class limits, and I'll show you that example here in a second. So here's 52 months or 52 individuals asked how many text messages they sent. Now again, this is discrete data. You're thinking, so why aren't we doing this the other way? Well, you also will do class widths with discrete data if your data is too spread out, right? I mean, if you look at all this and you put them, each individual number into a table, most of them would be ones. And it's too cumbersome. It's not really going to tell us much when you've got 52 rows of ones, right? So instead you want to group them together. And when you have a big set of data like this, you need to figure out, okay, how best to group it. Well, normally you want to come up with a nice little systematic way of doing it. So the best thing to do is look for the smallest and biggest numbers in your data set. And in this case, 130 was smallest and 399 was the biggest. Now, based on that, you want to figure out how wide your classes, each class interval should be. And the rule of thumb is you want to aim for somewhere between 5 to 20 classes, because anything smaller than 5, you're going to just have too many in each, and it's not going to give you a good picture. Anything more than 20, it's going to get too spread out, and you're going to get really small frequencies, and again, it's not going to tell you much. So you shoot for somewhere in between there. Here we only had 52 pieces of data, so around 5 would be the best, because you have roughly 10 in each class, if they were evenly distributed, which of course they're not. Okay, well, the difference between our low end and our high end was roughly 270, right? We had 130 to 399. So let's just say 130 to 400 is 170. So if we took, 270. If we took 270 and divided it by 5, it's a little bit more than 50. So let's go ahead and go with 50. We'll end up having 6 classes, but that's fine. So we're going to start with a width of 50, and we're going to start with our lowest value of 130, and we're just going to build from there, right? So you start at 130 and you add 50 to it. You can see that, remember, our last one was 399, so it's going to be most likely in this class. This one will probably end up just lopping off at the end. But now you can see that the class widths are 50, because the difference between 130 and 180 is exactly 50. Then all we have to do is fill in the top values, right, the upper class limits for each thing. And since the next one is 180, we have to subtract 1 from that, and then it's 179. Now we do this because, again, we have discrete data, and there's no such thing as 179.5. If you had continuous data, it would go 130 up to 180, and then 180 up to 230, and you would just have like a less than or equal to 180 for this first one. So you would know that you would have everything from 130 up to 179.99999, because you would say 130 and then up to less than or equal to 180. And then the next interval would be 180 up to less than or equal to 230. So that's how you would do this if you had continuous data. But as we see that we lopped off that last one because we didn't need it, because from 380, when we go up, 50, we get to 429, and that includes our largest one. So we kind of just forgot about that last one. We didn't need it. Then you go through your data and you count up how many are in each of those intervals, and you write the numbers down, and there you go. There's your frequency table for what's called grouped data or classed data, data in classes. Okay, let's look at another example. They surveyed the residents of San Francisco, about 17 million, interregional daily trips that the population takes. And along with other data they collected, they asked people to identify where their trips originated and how long they traveled. And the following table organizes that. So you can see travel time, home-based work, home-based shop, blah, 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 right? Lots and lots of data. Well, you can see in these intervals, going from 0 to to 5.1, or 0 to 5, and then 5.1 to 10, and then 10.1 to 15. There's kind of a difference, right? Here you go from 0 to 5.1. Here you go from 5.1 to 10.1, 10.1 to 15.1. So you can see that the class width for all of these is 5, but the class width for this one, this first one, is 5.1. It's a little silly. We normally want our classes to all be the same. Same thing here at the end, right? We go up by 5, but then we go up by, I don't know, I guess anything over 90.0, but then up to forever, right? So this last width could have an infinite class width. So sometimes the first class and the last class might have slightly different widths just to make everything logical. Now you could have obviously fixed the problem of the first one being different if instead of 0 to 5 and then 5.1 to 10, you just went 0 to 4.9, 5 to 9.9, and so on and so forth. But I can see why they do it this way, because they want to know how many people, traveled more than 5 minutes up to 10 minutes, more than 10 minutes up to 15 minutes, right? So it kind of makes sense. But anyway, we can still answer questions. How many classes are there? You could add them all up and see that there's 19. You could find the class width, which we could see was 5 minutes for all of the classes except for the first and the last one. Which guideline is ignored? Well, obviously that's the guideline that says we're supposed to have all equal widths, because the first one and the last one were a little bit different. And finally, not finally, there's one more. Which class contains the largest number of school-related trips? You'd have to go back and look through them and see that it's 10.1. And then same thing here when they ask, is the statement most people take 10 to 15 minutes to travel to school, is that true? Well, no. Just because that interval, the 10.1 to 15, had the most pieces of data in it, that doesn't mean most people, because most people means more than half, right? When we say most of a group, that means you have to have more than half of it being that. And if you look at the totals and take half of that, it's nowhere close to what was in this category. So that statement would not be true. All right, let's try a skill check, right? Use the distribution to determine how many people actually do take between 10.1 and 25 minutes. Well, you would have to add up the numbers from this one, and this one. All right, so take a second and do that. Did you get that number? All right. A pie chart shows how large each category is in relationship to the whole. It's a nice way of showing relative frequencies as a picture. And then a bar graph is usually used for categorical data. You can also use it for discrete data, because each individual bar is supposed to be separated by a gap. And there is a gap between 1 and 2 and 3 and 4, that kind of thing. And then the height of each bar represents the amount of data in each category. So here's a typical example. It's a horizontal bar graph, which is fine. They can be horizontal or vertical. And you can see that this is each group. You're just counting up how many of these things, right, are available. So it's not discrete numerical data, it's categorical data, which is what we talked about, that it can be categorical data. You can easily scan the graph to see that the silent generation is the largest percentage of approval amongst its age group, 64%. And you can see that quickly because it's the longest bar. That's the upside to bar graphs, is it visually tells you a lot of relationship advice, right? You can see that silent is the most, right? Millennial is the least, and so on and so forth. So, which has the second largest? Again, it's really easy to see that it's the boomers with 50. Okay, a side-by-side bar graph is just a bar graph where the bars are placed next to each other to show similarities or differences between two different populations. So here's an example where we're looking at the Surveillance, Epidemiology, and End Results Program of the National Cancer Institute provides information on cancer statistics. In order for their results to have the best impact, they need representative samples of the U.S. So in this case, we have SEER areas and then United States. And then what they did is they took each of those populations and they've got, okay, how many are foreign born in each of those? Less than high school diploma in each of those. Below poverty level in each of those. So don't get caught up in what the hell it means to be a SEERS area versus the United States. Just know that when you're basically comparing how many things you have with a certain characteristic in two different populations, then you do a side-by-side like this. A simple example would be, if you wanted to look at voter preferences amongst two different states. The blue state could be, let's say, Washington, and the orange state could be Oregon, since they're right next to each other. And instead of these things, this could be, Democrat, Republican, and independent. And then you could see how the distributions of registered voters is comparative between the two states. That's what a side-by-side side-by-side bar graph does. And here's some information, right, that we should have gleaned from looking at it. Now, a stacked bar graph is one in which you have one bar for each population, and they're stacked on top of each other. It compares different categories, but also how the whole of each category is broken down. So it kind of like shows the percentages within each category. It's not a real popular graph. I personally don't like them. They get to be kind of confusing, and a lot of people don't understand what they're seeing when they look at them. Now, a histogram is a bar graph that we use when we have continuous data, right? Because the bars are all stuck together. So here's that continuous data, right, where we have a range, and then the next one has another range, and so on and so forth. So you can see there's no gaps in between the bars. But we can also see that 60 to 119 had the highest frequency, and it looks like 840 to 899 had the smallest. And then we could answer all sorts of questions about it. Approximately how many drivers waited between the 60 and 180? Well, we would have to count up the frequencies for this bar and this bar, right? These two bars here. So almost 50 plus almost 30. And then so on and so forth, right? We could answer all of these. Approximately how many drivers waited more than 7 minutes? We had to figure out, okay, 7 minutes, 6 times 7, right? And then figure out where that is on the scale, and then add up everything more than that. If we wanted to determine the number of drivers surveyed, we'd have to add everything together. So there's the first one, right? Second one, third one. So 241. For part B, between 60 and 180, right, we would add up the 48 and the 28 and get that answer of 76. For C, where they want to know the number of drivers who waited more than 7 minutes, we have to, again, convert it to 420 seconds. And then go over here and go, okay, 420 and above, right, would be all of these numbers, 15 plus 9 plus 8, blah, 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 add them all together, 95. Although 420 seconds represents the middle waiting time for the classes, it is inaccurate to say that half of the drivers recorded time is less than this time and half recorded more, because as we saw in the previous example, 95 were 420 and above, but there was a total of 241. So the middle class is not necessarily the middle of your data. Just keep that in mind. If we add the first two classes together, we get 63. If we add in the third, we get 91. Continuing with the fourth, we get 110. Halfway is 120, right? So we're not quite there. So we include the fifth class, which gives us 17 more. That gets us to 127. So the fifth class has a lower limit of 240. So it's more accurate to say that about half the drivers waited more than 240 seconds, because we know half of them are within, right, this class or below, and the other half are within this class and above. So you could say, 240 is the break point. You could take the midpoint of this, right, and basically say 270, rough. So half were below 270 and half were above 270, that kind of thing. But when it's in this kind of representation, you don't actually know the specific value, so you can't give a specific answer for what the median is, what the middle value is. A line graph shows how data changes over time, so it's usually called a time series graph. Here's an example of census data. And we can see a distribution, in this kind of picture. So this is another visual representation of not a typical graph. It's just a map with colors, right? being able to read the graphs, which state had a higher slave population than free population in 1860. Well, you could go through here and you could look at the differences between free and slave and go, well, if percentage of slaves is over here, we know that if this is greater than 50, then there's going to be a larger slave population than a free population. So we can see it's those two states. And then, the rest of these we can answer again by just doing some simple math, which had the highest number of slaves, right? You go back and just observe it. Only 30% of its population slaves. Virginia had the highest slave population, right? So even though the percentage was low, it still had the highest population. That just means they had a lot of other people. The reason why maps like this are popular is the visual is really powerful, right? The colors are a really strong visual representation. You can really see where the things are happening, in this case where the slavery is higher and lower, right? So like if this was instead a map for current day problems like pollution, you could see where the pollution was the highest, so where you would want to put your resources at trying to fix it. And that's all I got for you.